Hello learners, on behalf of Indira Gandhi National Open University, we welcome you for this video lecture session. Today's topic is Cogeneration Plant. This is the 27th module of the course Thermodynamics and its application. I am Subhasis Maji, Professor in School of Engineering and Technology from Indira Gandhi National Open University. Today's topic is Cogeneration Plant. After listening to this video lecture, you will be able to understand the concept of cogeneration plant. You will be able to appreciate the classification of cogeneration system, and also you will be able to explain the types of cogeneration system. First of all, let us discuss what is cogeneration. Definition of cogeneration is where a fuel source, for example gas and biomass, produces energy, for example electricity, at the same time as producing thermal energy, as an example heat, in one process. Cogeneration means cogen, that is CHP, combined heat and power. So today's discussion will be on cogeneration system. Cogenerations or combined heat and power, that is CHP, is defined as the sequential generation of two different forms of useful energy from a single primary energy source, typically mechanical energy and thermal energy. Mechanical energy may be used either to drive an alternator for producing electricity or rotating equipment such as motor, compressor, pump or fan for delivering various services. This is the block diagram of cogeneration system with condensing steam turbine. In this process, there are important components like boiler, which is producing high pressure, high temperature steam, and the heat we are getting by burning of fuel inside the boiler, and that high pressure, high temperature steam is entering into the turbine, and inside the turbine expansion of steam takes place, and in turn turbine does work. The shaft of the turbine is coupled with the shaft of the generator, and in turn generator produces electricity. Now you see that in between we are tapping some steam from the steam turbine which goes to the process heater. So steam to process, and thereby the heat is given out and we get thermal heat for the processes which are required for any industries like chemical industries, cement industries, textile industries, where heat is required, and that heat we can get from the steam turbine, either tapping or extracting heat in between the processes of turbine work, and that heat we can utilize as a process heater. After that, the low pressure and low temperature steam, after expansion in the turbine, that enters into the condenser, thereby in the condenser it is condensed into liquid water. But in the process heater, when the heat is given out to the process, after that, that steam may be condensed into liquid and it is sent back to the condensate tank, and in the condensate tank we get only fluid in liquid form. So the liquid water from the condensate tank is sent to the boiler with the help of a pump. So this is the schematic diagram for the cogeneration system with condensing steam turbine. This is one of the diagrams for cogeneration system with closed cycle gas turbine. In the gas turbines, the main components are compressor, combustion chamber, gas turbine and generator. In the compressor, the air is compressed and the compressed air is sent to the combustion chamber, and there is fuel injected or fuel is given in the combustion chamber as a heat source, and the high pressure and high temperature combustion gas comes out from the combustion chamber and enters in the gas turbine, and the gas turbine shaft is coupled with the shaft of the generator. In turn, generator is producing electricity. The high pressure, high temperature gases which comes out from the gas turbine passes through the heat exchanger, and here the heat of the high temperature and low pressure gases gives out to the water which is being heated and sent back to the process, and the air which comes out from the heat exchanger is entering into the compressor that completes the cycle. The conventional method of power generation and supply to the end customer is wasteful, as only about a 1/3 of the primary energy fed into the power plant is actually made available to the user in the form of electricity. In conventional power plant, the efficiency is only 35% and remaining 65% of energy is lost. The overall efficiency of the energy used in cogeneration mode can be as high as 85% and above in some cases. Now let us take an example. Suppose we have the energy from the fuel as 100 unit. Out of 100 unit of energy available, 60 unit of energy will be used for the power system whose efficiency is 45%, and 40 unit we will use for heating in boiler, and the boiler efficiency is 80%. Now let us see what is the output for the available energy in fuel, that is 100 unit. For power station, 60 unit is given, so efficiency is 45%, so 60 into 0.45 is equal to 27. So 27 unit of energy we are getting as an output from the power stations. Now for heating of boiler, 40 unit is given and the efficiency of the boiler is 80%. So 40 into 0.8, that is 32 unit of energy. So 32 unit of energy we are getting from the boiler. Now total energy we are getting as an output is 27 plus 32, that is 59 unit out of 100 unit of energy at the initial stage. So there is loss of 41 unit of total energy which was initially given as 100 unit. But if we utilize a cogeneration plant, combined heat and power plant, so in that case, if we want to get as an output 27 unit of energy as an electricity and 32 unit of heat So total is 59. So if the efficiency of combined heat and power plant is 84%, so 70 unit we have to give as an input, because 70 into 0.84 is equal to 59, and out of 59 we can bifurcate as 27 for electricity generation and 32 for the heating process. But in this case we are getting as an output from cogeneration plant 59 and input is 70 unit of energy. So the loss is only 11, that is 70 minus 59 is equal to 11. So in this case it is clearly shown that the loss for CHP is only 11 unit, whereas if we separately use for generating electricity of 60 unit out of 100 and 40 unit we use for heating in boiler, so that we can get 59 unit as an output, but in that case the loss is 41. So definitely we must use the cogeneration plant, that is more economic. Now let us discuss the same point for your more clarification. Let us consider one example. Just now we have mentioned, suppose a chemical industry requires 27 units of electrical energy and 32 units of heat energy. The primary energy input in power plant will be 60 unit and 27 by 0.45, that comes out to be 60 unit. That means if we give 60 unit as an input, then if the efficiency is 45%, we will get 27 unit of energy as an output through separate heat and power route. If a separate boiler is used for steam generation, then the fuel input to boiler will be 40 units and we will get as an output 32 unit, because the efficiency of the boiler is 80%. If the plant had cogeneration, then the fuel input will be only 70 unit, and if the efficiency is 84%, we will get 59 unit of energy as an output. The total loss, which was 41 units in the case of separate heat and power inputs, has now reduced to 11 units in cogeneration mode. Along with the saving of fossil fuels, cogeneration also facilitates reduction in the emission of greenhouse gases, particularly carbon dioxide emission. Now let us discuss about the classification of cogeneration system. Cogeneration systems are normally classified according to the sequence of energy use and the operating schemes adopted. Classification of cogeneration system. Cogeneration systems are basically two types: topping cycle and bottoming cycle. So these are the diagrams shown for topping cycle steam and bottoming cycle steam. In the topping cycle steam, say the fuel is used for the prime movers and the electricity is generated. That means the first priority is for producing electricity, and the heat extracted from the steam which is coming out from the turbine, we can use that steam in a process heater, and if this is the scheme, then it is known as the topping cycle. But in the bottoming cycle is the fuel is used for boiler, and the boiler is generating the thermal energy. In some industries like cement industries, chemical industries, textile industries, they need thermal energy, and the first priority of using that thermal energy in different industries, and the waste heat which is recovered, that can be used for generating electricity. And if this is the process for which the priority is the heat which is being produced in the boiler is used for the different processes as a thermal energy, and if this is the priority, this cycle is known as bottoming cycle, and the byproduct energy which we get as a waste heat, that can be used for generating electricity. And this bottoming cycle is generally used in big industries like cement industries. In the topping cycle, the fuel supplied is used to first produce power and then thermal energy, which is the byproduct of the cycle and is used to satisfy process heat and other thermal requirement. In the bottoming cycle, the primary fuel produces high temperature thermal energy, and the heat rejected from the process is used to generate power through a recovery boiler and a turbine generator. Typical areas of applications include cement, steel, ceramic, gas and petrochemical industries. Topping cycle cogeneration is widely used and is the most popular method of cogeneration. The two types of steam turbines mostly widely used are back pressure and extraction condensing. The choice between back pressure turbine and extraction condensing turbine is driven mainly by the quantity of power and heat, quality of heat and economic factors. The extraction point of steam from the turbine could be more than one, depending on the temperature level of heat required by the process. Now, see, if you use the steam which is coming out after the expansion in the turbine, and that is having some saturation temperature. So with that temperature, the water can be used in a process heater. But sometimes the heat required is more. High temperature steam is required for the heating process in some industries. So in that case, we have to extract steam at different points as per the requirement of the thermal heat required by the industries. We have to extract that steam at that particular point from the steam turbine. The main advantage of using steam turbine over other prime movers is the option of using a wide variety of conventional as well as alternative fuels such as coal, natural gas, fuel oil and biomass. The power generation efficiency of the cycle may be sacrificed to some extent in order to optimize heat supply. This is the block diagram of simple back pressure. So here the boiler is there for generating high pressure, high temperature steam. That high pressure, high temperature steam enters to the turbine and expansion of steam takes place in the turbine. Thereby, turbine does work and the shaft of the turbine is coupled to the shaft of the generator, which in turn produces electricity. Now the low pressure steam, instead of passing through the condenser, here it is passing through the process heater, and the heat is given out to the circulating water in the process heater, and that water receives the heat from the steam and thereby its temperature increases, and that hot water is being used in the industries. After that, it is sent to the boiler with the help of pump, and that completes the cycle. In this case, we are assuming W kg per hour steam passing through the cyclic process. This is the TS diagram of cogeneration power cycle. Here, point 1 is the entry point of the high pressure, high temperature steam entering into the turbine. Here, the rate of mass flowing through the cycle is W kg per hour, and exit point of the turbine is point 2, and 2 and 3, these are the state 2 and state 3 of the process heater, and 3 is the entry point of the water, the pump, and 4 is the exit point of the pump. So here you see that in this diagram it is very clear how to calculate the turbine work, how to calculate the process heat required, and how to calculate what is the fraction of energy utilized for this cogeneration power plant. Now see, WT is the turbine output in kilowatt. QH is the process heat required in kilojoule per hour, and small w is steam flow rate in kg per hour. Now WT into 3600 is equal to small w within bracket H1 minus H2. Here we are multiplying 3600 because turbine work is given as an kilowatt, that is kilojoule per second. We have to convert into kilojoule per hour. Now W into H2 minus H3 is equal to QH, that is heat given out to the cold water for heating up, which can be used in the industries in the process heater. Now we can write WT into 3600 is equal to QH divided by H2 minus H3 multiplied by H1 minus H2. From this expression you can find out QH, the heat given out from the cogeneration plant for the process heating. QH equal to WT multiplied by 3600 multiplied by H2 minus H3 whole divided by H1 minus H2. Fraction of energy of Q1 utilized in the form of work WT and the process heat QH in the cogeneration power cycle equal to WT plus QH whole divided by Q1. In the cogeneration power plant, the condenser loss is 0 because we are not using condenser. Instead of condenser, we are using the process heater, and in this case, the fraction of energy utilized is maximum. The efficiency of a back pressure steam turbine cogeneration system is the highest in cases where 100% back pressure exhaust steam is used. The only inefficiencies are gear drive and electric generator losses and the inefficiency of steam generation. Therefore, with an efficient boiler, the overall thermal efficiency of the given system could reach as high as 90%. This is the diagram for extraction condensing steam turbine. What is the need of extraction condensing steam turbine? Sometimes the heat required for the chemical industries for different process is more. So definitely we have to extract steam from the turbine as per the requirement of thermal heat. So here there is extraction of heat and it is being passed through the process heater and heat is given out to the water in the process heater, which is being used for the process industries, and after giving out the heat it will be transformed into water and it is being sent back to the boiler with the help of pump 1. Now the remaining steam after the extraction point will expand in the turbine for producing work, and at the end of the process inside the turbine, the low pressure, low temperature steam will pass through the condenser. It is condensed into the water and the pump 2 sends the water to the boiler, thus complete the cycle. In this type, steam entering at high or medium pressure is extracted at an intermediate pressure in the turbine for process use, while the remaining steam continues to expand and condenses in a surface condenser. In two-stage extraction cum condensing turbine, medium pressure steam and low pressure steam pass out to meet the process needs. In an extraction cum condensing steam turbine system, the steam for the thermal load is obtained through extraction from one or more intermediate stages at appropriate pressure and temperature. The remaining steam is expanded in the turbine. In a two-stage extraction cum condensing turbine, medium pressure steam and low pressure steam pass out to meet the process needs. In an extraction cum condensing steam turbine system, the steam for thermal load is obtained through extraction from one or more intermediate stages at appropriate pressure and temperature. The remaining steam is expanded in the turbine. Now we will talk about the gas turbine cogeneration system. So here there is a compressor for the gas turbine, there is a combustion chamber, we call it combustor in the gas turbine cogeneration system, and obviously there will be a turbine which generates the electricity. Now let us discuss the process. In the compressor, air is being compressed and the compressed air is sent back to the combustion chamber and fuel is injected to the combustion chamber and the burning of gas takes place, and the high pressure high temperature gas comes out to the compressor and enters into the turbine, and there is expansion process takes place in the turbine, thereby turbine produces work and the shaft of the turbine is coupled with the shaft of the generator, which in turn produces electricity. Now the hot gases coming out from the turbine is used for the heating purpose in the process heater, and after that when the heat is given out to the process heater, then it leaves the process heater as an exhaust gas. Obviously that temperature will be much less than the hot gases coming out from the turbine. So this is known as open cycle gas turbine cogeneration. Gas turbine cogeneration systems can produce all or a part of the energy requirement of the site, and the energy released at high temperature in the exhaust stack can be recovered for various heating and cooling application. Though natural gas is most commonly used, other fuels such as light fuel oil or diesel can also be employed. The typical range of gas turbines varies from a fraction of a megawatt to around 100 megawatt. Gas turbine cogeneration has probably experienced the most rapid development in the recent years due to the greater availability of natural gas, rapid progress in the technology, significant reduction in installation cost and better environmental performance. Gas turbine has a short startup time and provides the flexibility of intermittent operation. Now dear learners, we have discussed in detail about the cogeneration plant. Now let us summarize our discussion very quickly. We have discussed the concept of cogeneration plant. We have discussed the classification of cogeneration system. We have discussed different types of cogeneration system, and we have also discussed the different applications of cogeneration system. Thank you very much.